So, we've now seen a lot of Core Spark, but we haven't yet seen one of the mechanisms that brought it notoriety. Its caching mechanism. It's this ability to store intermediate data in memory while keeping it distributed that allows it to boast the possibility of a 100 times performance gain over Hadoop. This can be useful for a number of scenarios, but especially for iterative algorithms such as those common in machine learning, as well as a means to quickly experiment with data in the shell. So, how does it work? To understand it, we'll first take a look at what we already know. Here we have a simple RDD, which we want to run through a performance-intensive algorithm, which we'll simulate via a thread.sleep. The results are used to create a new RDD containing the transformed data. Then, we run another, quicker transformation to get our final RDD. Okay, we should already know all of this. However, one thing you might have noticed while running some of the examples earlier in the shell, no matter how many times we reran our code with the same or shared lineages, the results still took just as long, mostly bottlenecking on the initial data load and cleanse. Since RDDs are merely instructions for what to do, each action requires a completely new execution so that the data can be pulled into the system. So, suppose that we'll be working with the slower to load RDD numerous times. We don't want to have to wait for the full load each time. So, we call the RDD's cache or persist method. This is the same as a transformation in that it merely instructs the RDD to cache the data at this point. Nothing will be actually cached until an action is performed. However, unlike transformation methods, this returns the RDD back instead of a new one. So, you can opt to use the returned RDD or the same one you called cache on. They're both the same object. There are even different levels of caching, with the default being to store the data in memory, but you can also choose to either use or combine with disk storage. You might think there's no point to storing to disk, as that's often the bottleneck. But even as our example shows, there are cases where the algorithm itself is the bottleneck, so at least storing to disk is better than fully rerunning the DAG. So, now we can execute the code for the first time after adding the cache directive. It'll run from the start, and once it hits the RDD to be cached, it'll store it off for future executions. Then it continues on as it did the first time. Now, we want to run a new transformation against our data. This time, the execution graph realizes that it can skip the slower instructions and grab the data directly from the cache. The beginning instructions remain there only for the case of fault tolerance. If the cache is lost for any reason, then that portion will be recalculated and recached. The rest of the transformation works normally. The RDD is abstracted enough such that it doesn't care where it's pulling the data from. So, let's see this in action. We're back in the shell with our tokenized wiki RDD. Once it's marked to be cached, we can call our distinct count again. Remember that the first action runs as normal, caching where necessary along the way. This takes about 6 to 7 seconds on my machine. Now that it should be cached in the second run, it returns almost instantaneously. We just saw the cache method in action. However, this is just an alias for the persist method. Both use the default storage type of memory only, meaning the data will cache to memory, and anything that doesn't fit in memory will require a full execution to create the entire RDD. However, persist can also accept a parameter specifying the level of storage to use. There are a number of storage level options. We've already seen the default, memory only. Next, you can specify memory and disk if you want to use memory with overflow saving to disk instead of requiring a full execution. Then is disk only, which is exactly as it sounds, storing the intermediate data only to disk. And if memory space is an issue, then you can append _SER to the memory options so that the stored data will be serialized, obviously taking a serialization performance hit in favor of the smaller size. And all of these options can be appended with an _2 so that the data is replicated to another worker. This limits the need for full recomputation upon failure, as the DAG scheduler can opt to use the alternate storage location, which will re-replicate the data. The final type is off-heap, which stores the data in memory off the JVM heap. However, this is still listed as experimental on the website's documentation, yet oddly not in the API documentation. So I wouldn't deem it battle-hardened. There's also a none storage level, however that's the default setting for any RDD, so using that storage level would be a zero-sum gain. Now that we've seen all the different ways to cache the data, what about if we're done with a cached RDD? We can call the unpersist method to clear the cache. If called with empty parameters, it'll default to blocking the execution thread until the memory is actually cleared. However, you can always pass in false to denote that the execution move on to the next piece of code without waiting for the memory to be cleared. But this call to unpersist is not required, as the cache should clear itself once the RDD falls out of scope, or will be evicted by a more recent RDD due to its defaulting to a least recently used eviction strategy. And to close out this section, there are a couple of side notes. Unlike other methods that we've seen and used, the unpersist method is built such that the parentheses are required in the empty parameter scenario, or else it won't compile. And once an RDD marked for persistence is acted upon, then it cannot have its persistence level reset without first calling unpersist.